Hi, everyone. Thanks for being here. And thank you also for the local organizers for putting this together despite all the difficulties. I'm sure it's been quite tough, but you still keep the event rolling, so this is excellent. So I'm going to talk about this paper that you can find on the archive there. This is about this work that you can find on the archive and hopefully somewhere else soon. And it's a joint work with Yuri. He's in Auckland, New Zealand now. And on the other end is Laura, who's in Copenhagen. And at the time, both Sigurd and Chen were Laura's student. Chen has now graduated. And Chen is also here, so you can also talk to Chen about this if you're interested and can't find me. So, we're talking about randomness, right, and quantum randomness. So you might imagine, what can I do to extract some randomness from a quantum state? Well, I can take a superposition, let's say, of the computational basis states, and I just measure in the computational basis, right? This gives me like a uniform bit, and that's end of story, right? So, thank you for your attention. This is how you get quantum randomness. But then you might have heard people say, when you start talking about randomness, right? So it's random, but random for whom? Right? This is a common question. So you might imagine a different scenario where you have this state, which is an entangled state. Let's say you hold one of the qubits. You measure this one qubit in the computational basis. You get the same uniformly random bit. And you might think, okay, I'm happy. I have this random bit. I have my randomness. But if someone else holds the other qubit and they measure in the computational basis, they will get the exact same random bit. So now it's random for the two of you, right? And this is not necessarily an ideal situation if this other person is an eavesdropper who wants to know your random bit. So if you don't trust your state and or your measurement, you can run into some problems. And this is what device independence is about. I don't want to actually trust that I have this state or the previous state. I want to be able to prove that I have private randomness just from observable things. And the framework we use for device-independent randomness is Bell non-locality. I already added an eavesdropper into my Bell non-local scenario, but what we have in general is two honest parties, Alice and Bob. So the black boxes are the honest users who are trying to generate some randomness. And there is a third party, Eve, who is trying to listen in and guess the random bits or dits. And in general, we can imagine there's a tripartite state psi shared between these three parties. But what Alice and Bob see are these correlations. So they have some outcome probabilities. So they measure some measurements, which are labeled by X and Y. And given this X and Y, they obtain some outcomes, A and B. And if you believe in quantum mechanics, and this is what we're going to do for this talk, then we know from Bohr's rule that the probabilities of these outcomes are given by this formula, right? I have some state, rho, which could be a mixed state, right? This is like the partial state, this bipartite state between Alice and Bob. We have some state rho, and then we have these POVMs, A and B. But crucially, we don't assume that we know what this rho is, and we don't assume that we know what these measurements are. The only thing we trust are these correlations, the probabilities. This is something that you can, click the buttons on your device, record the outcomes, and then estimate these probabilities. So this is something you can trust. And once you collected these statistics, you might want to ask, well, what is the randomness generated by some measurement? And for simplicity, we will fix just one measurement. Let's say I want to extract randomness from one of the measurements of Alice that I call X. And the way to measure this randomness is through the conditional von Neumann entropy. So this H is the von Neumann entropy of Alice's classical variable, which I just call A now here. And E is all the quantum information that Eve might have. So to formalize this a little bit more, we want to calculate the conditional von Neumann entropy of this classical quantum state. Right? So these A's are the potential outcomes of Alice, and we collect them in these like classical states. And this, the second tensor factor here is just the the quantum state that Eve holds after Alice measured X and obtained outcome A. So the private randomness is characterized by this conditional entropy, right? What is the uncertainty left in this variable A once you condition on all the quantum information E that Eve has? And importantly, okay, somehow, well. So importantly, we want to minimize this quantity, this conditional entropy, in a way that is consistent with what I can actually observe, which are these correlations, right? So I only trust these correlations, and I want to minimize the conditional entropy over all possible states and measurements that are compatible with what I see. And this is, of course, in general, quite difficult, right? I only see the probabilities. I want to put a bound on this entropy. And this is the task of device-independent randomness. Right, and the slightly more specific task that we looked at in this paper is how much randomness can I certify device independently if my quantum state is locally d-dimensional, right? So I don't trust the quantum state. I don't actually even trust the dimension of the quantum state, but I'm curious. Let's say I know I can, in principle, prepare a locally d-dimensional entangled state. How much device-independent randomness I can hope to extract from it? Sorry, I don't know how to make the start bar go away. Oh, I did it. Okay. So if the question is not device independent, then, well, I can generate as much randomness from it as I want because I just toss a coin, or like an n-sided coin. I can get as many bits as I want, but device independently, there's a limit on this. And this essentially comes from the convex structure of POVMs in a given dimension. Right, let's say this A sub A is an element of some POVM. Now, if I can write it as a convex combination of some other POVMs, right, this right-hand side is again a POVM. So this is kind of this convex structure. Now, if I have a convex set, I can think about the extreme points of this set. And it was shown that the extremal POVMs in dimension D have at most D squared non-zero outcomes, right? So this is going to be important for this bound, because what we want to do is minimize this conditional entropy. So this is kind of a sketch of a proof. If I have a POVM A and I want to extract my randomness from that POVM, if I can decompose it as a convex combination of some other POVMs, then the conditional entropy will be smaller than the convex combination of these individual conditional entropies I can get from those POVMs. And then this is fairly simple. So now the conditional entropy is smaller than the non-conditional entropy. So I get to here. And each of these are extremal POVMs with at most D squared non-zero outcomes. So these have at most, this entropy is at most 2 log D, each individual one, right? So at the end of the day, we end up with this statement that if I have a locally d-dimensional state, the maximum entropy I can hope to certify from this device independently is 2 log D. And then the question arises, well, can I always achieve this much entropy? Can I do this in every dimension? And this was only known in dimension 2 and 3. And somehow the footnotes match up with the numbers, which is very nice. So these are in these 2 papers. But it was not known for general dimensions, right? And this was a question we wanted to answer. And maybe just a useful remark, or maybe something to think about if you're like a bit more familiar with non-locality and self-testing. A POVM with D squared outcomes in dimension D is necessarily non-projective. So when we want to certify these kind of measurements, it's going to be a bit more difficult than like your usual, let's say, self-testing statement. We are really looking for non-projective measurements. So what is the state that we want to, So what is the technique that we use to certify this randomness device independently? So we saw that there was this minimization over all possible states and measurements. This is very difficult in general. So what we use usually is a Bell inequality, which is just a linear functional of these probabilities. And this is now just notation. So we can use these, what people usually call Bell operators, but it's like an operator valued function. So this is the Bell operator that corresponds to the Bell inequality. I just replace the probabilities with some operators. And so the relation between these two quantities is that if I have a value of a Bell inequality, I can get this from the state and the measurements by plugging the measurements in this Bell operator and taking the trace of the Bell operator with my state. And this is just useful for defining the sum of squares, which is if I can write my Bell operator, so I have some beta times identity, and I subtract the Bell operator. If I can write this object as a sum of squares, so these Q's are again some operators that are functions of my measurements. If I can write this as this sum of squares, this implies that the value of this Bell inequality, which is again just this trace as we saw here, is bounded by beta, which is this beta from the sum of squares. Right, so okay, maybe you're familiar with this, or if not, if you look at this long enough, you can convince yourself. If not, just believe me. So this is a way of getting bounds on Bell inequalities, but more importantly for us, this means that if we do reach this beta value exactly, that implies that all of these QJ operators that we use in the sum of squares, when they act on the state, we need to get 0. This is the only way to saturate the inequality. And so this, like orange relations, you see these are relations between the measurements that you use and the state that you use. So you get some information about the measurements and the state only from observed correlation, right? So this is what you observe, that the Bell inequality value is beta, and from this, you can deduce some things about your state and your measurements. And this is how we can certify things about our setup. And this is what we use. And the setup we want to certify is a maximally entangled state in dimension D. So this is kind of a good candidate for potentially generating randomness. And the class of measurements that we call balanced informationally complete, or BIC-POVMs. So these are D-squared outcome POVMs on D-dimensional Hilbert space, and they have this form that they are these subnormalized projections. So the PJ are rank 1 projections, and they form a basis for the operator space. So this is a class of measurement that we introduce in our paper, and it was already shown in this other paper that these actually exist in every dimension, and we also construct them in our paper explicitly. So you can kind of see why we want this setup, because basically what we want is to measure half of the maximally entangled state with a D-squared outcome POVM such that I get all outcomes with equal probability. This is a sort of first requirement to get D-squared bits uniformly. And the way we do it is through Bell inequalities and sums of squares. So we have this slightly complicated looking Bell scenario. It's not super important. What's important is that on Bob's side, we have these D-squared measurements, which are projective and binary. And on Alice's side, we have a bunch of measurements, but there is one important measurement that we call POVM. And this is the one that we want to use for randomness extraction. And we find Bell inequalities that are parameterized by D, which is going to be like the dimension that we want to use. And it's parameterized by a BIC-POVM with given overlaps, which is just like the trace of these projections from our BIC-POVM from the previous slide. And what we can show through the sum of squares techniques is that to get the maximal violation of our Bell inequalities, Bob's operators must satisfy these things. So they have to be projective, they add up to D times the identity, and they satisfy these kind of sandwich relations. And if you had more time to look at the slides, you could convince yourself that actually these BIC-POVMs, the operators, they satisfy these relations. And so basically you can generate an algebra from these relations, And essentially what this says is that the maximal violation certifies that Bob's operators are a representation of this BIC-POVM algebra. And I think I will run out of time, so I will not show you the details of the last slide, but basically we use the representations of this BIC-POVM algebra to then certify enough about our setup to get the 2-log-D randomness bound, right? So we can say some things about our state. We cannot say that it's exactly the maximally entangled state, but there are some maximally entangled states hidden in there. And this POVM measurement has a form that's, again, not exactly what we want, but it's enough. You're essentially measuring these C operators, which are also representations of this BIC-POVM algebra, on these maximally entangled states. There's many of them, but just the relations that we have for these operators are enough to actually certify that you have the desired amount of randomness. Right, so I'm not going to go through like this slide because I'm running out of time. So I'm just going to summarize instead. So basically what we need is device-independent randomness if you really want true privacy of your random bits. And there's a fundamental bound on how much randomness you can get from a locally d-dimensional system. And there's a candidate measurement and state that generates this randomness, and we can certify this through a sum of squares decomposition. Importantly, if you know what a self-test is, this is not a self-test, right? We kind of characterize our setup, but not completely. And of course, we remain with some open questions. So this was just local randomness, so just randomness from Alice's side. There's also a question of how much global randomness we can get if we also want to extract randomness from the other side. This was a completely idealized case, so there was no robustness. If you have some errors in your experiment, which is always the case, we don't know how the randomness scales with these errors. Some other questions is what other tasks we can use these BIC-POVMs in. And if you're familiar with SIC-POVMs, then, well, these representations of this BIC-POVM algebra might also be useful in trying to tackle the problem of SIC-POVMs, which is something to do in the future. And with that, I thank you for your attention.
Thank you very much for the talk and questions.
Thank you. Very, very interesting. Is this working? Yeah. When I heard you say that you had big POVMs for all dimensions, I immediately thought, oh, is this different from SIC-POVMs? So I guess it is different because so you don't have SIC-POVMs. It's still an open problem. What's the difference between BIC and SIC? I didn't get that.
Yes, thank you. So the difference is in the overlaps. So if you go to the definition of BIC-POVMs, so you have this d-squared outcome rank 1 POVMs that form a basis, which is basically saying it's informationally complete. But we don't say anything about the overlaps. For SIC-POVMs, the overlaps need to be uniform. So if you go like here, these overlaps, for SIC-POVMs, these are all the same. Whereas for us, we allow these to be anything that's compatible with the informationally complete property.
Sorry, compatible with what?
With the informationally complete property, so that the P operators need to span the space, which I think essentially means that none of these should be 1 unless J equals K.
One question.
Thanks a lot for the very nice talk. Maybe I missed this, but I guess you talked a lot about the algebra and so on, but did you mention if there's any conditions on the actual Bell inequality you need to use?
Well, yes, so for every D and for every BIC-POVM, you compute these overlaps, and then I can tell you what the Bell inequality is.
Okay.
I didn't put it on the slides because it's not particularly illuminating. I mean, it is in a sense, but it would take a long time. But I don't know if that answers the question. Like
it does. Yeah, I mean, as long as you have a method to figure it out and it exists, I'm fine.
Yeah, yeah, you can write it down. Once you have this D and you have these overlaps, you can just write it down. It's not too complicated.
Thanks.
Thank you very much for your very nice talk. So I have actually two questions regarding the algebra and the representation part. So my first question is that when you use this algebra theory for your results, do you rely on the property that this underlying state is a maximally entangled state? And the second question is, I think it is related to your open question part, so about the robustness. So can you kind of use the approximate representation theory to show some sort of robustness? So that is just my 2 cents.
Yes, thank you. So the first question about whether we use that it's the maximally entangled state. Eventually, yes, but there are steps, right? So first you can show these things about both measurements. Then from this, you find operators, which are basically these C operators on Alice's side. These are not actually operators that are in the experiment, but you can write them down in terms of operators that are actually featuring in the Bell experiment. And what you actually show that these C operators and the B operators intertwine the state. And from there, you can show that you have a bunch of these maximally entangled states through Schur's lemma. So this is kind of the order of things. So maybe the answer is no, it's the other way around. So from the algebra, you show the maximal entangledness. And the other question about robustness, yes, approximate representation theory, yes, this is something I would like to understand. So if you do understand this, then please talk to me, because I would like to hear about that. Thanks.
Great. I think there were last questions.
Thanks for your presentation. I have a question that why you consider the upper bound of the minimized entropy, because mostly we use the lower bound to extract randomness in a device-independent system.
Yes, thank you. Yes, so eventually we want a lower bound, but this, where is it? This chain of inequalities, this just tells you that what is the maximum you could hope for the minimum, right? So you're doing this minimization, and what I'm showing here is that whatever I do, I can never get above this 2 log d. So this is really just a kind of fundamental bound of what is the max I can hope for. Right, so eventually, at the end of the, at the end of the talk and the slides, you get the 2 log d also on the left side here. Right?
So let's thank the speaker again, and